Far out in space on an exoplanet known as Proxima b, scientists with the help of the new and powerful James Webb Space Telescope are watching out for lights which may be the final solid evidence that it's inhabited by aliens. However, that's not even the scariest discovery on Proxima b by the JWST. What terrifying new thing is this masterpiece of engineering discovered on Proxima b? How does it affect humans' chances of sending astronauts to this faraway planet? Join us as we dive into the James Webb Space Telescope's terrifying new discovery on Proxima b that changes everything. Mars gets attention as the next possible planet to host humans, with Elon Musk's SpaceX at the forefront of making it a permanent human base. At millions of miles away, Mars is relatively close to the Earth, making it a possibility to send humans there, even though such a mission is challenging. However, much farther out in the universe are a class of planets, which we shall soon focus on one of them. They are known as exoplanets. What are exoplanets? Exoplanets are simply planets that orbit a star other than our Sun. The prefix exo points to the fact that these planets are located not just outside, but far outside of the solar system. Astronomers have confirmed thousands of exoplanets revolving around these distant stars, and there are more yet to be confirmed. The first two exoplanets were discovered orbiting a pulsar in 1992, and the first one confirmed to be orbiting a star like the Sun was in 1995. The discovery of exoplanets is thanks to the more powerful scientific equipment available to us today. Exoplanets like Proxima b are difficult to detect for several reasons. They are very far away, separated from us by light years. Another problem is that, like the Earth, exoplanets don't send out light, but only reflect the light from the star that they orbit. So in contrast to their stars, exoplanets are very dim. Even the largest are drowned out in the light of their vastly brighter stars. That's why even the largest are too small to be glimpsed in optical telescopes. The discovery of exoplanets has made scientists realize one thing about our own solar system. It is an exception in the world of star-planet systems. Actually, before we started discovering exoplanets, most scientists expected exoplanets, if they existed, to be similar to the solar planets, but they encountered many different positions and orbits that are hard to explain. There are several types of exoplanets, including hot Jupiters, called as such because of their mostly gas content and mass similar to Jupiter. Then there are the super-Earths, which are planets with a mass between that of the Earth and the smallest gas giants, Neptune and Uranus, in our solar system. The composition of such planets is rock rather than largely gas, and so are more likely to be like the terrestrial planets Mercury, Venus, Earth, and Mars. Some exoplanets are mini-Neptunes with masses up to 10 times that of the Earth. However, they are not as big as Neptune. Exoplanets containing plenty of water are known as ocean worlds, while ice giants are exoplanets that are made up of volatile compounds such as water, methane, and ammonia, rather than the hydrogen and helium of Jupiter and Saturn. One of the reasons scientists study exoplanets is to see if some of them can host life. Of all the commonly known exoplanets, none commands as much interest as Proxima b, and the high level of interest will only continue with the new James Webb Space Telescope. Proxima b's existence was confirmed in 2016 and is located roughly in the middle of the habitable zone of the Proxima Centauri star. Its discovery was possible thanks to the high-accuracy radial velocity planet searcher, or HARPS, at the European Southern Observatory at La Silla, Chile. Proxima b's star, Proxima Centauri, is the Sun's nearest stellar neighbor, only 4.25 light-years away. Scientists decided on the name Proxima b using the naming convention used by planet-finding astronomers. It has the name of the star followed by lowercase letters, starting with B for the first planet discovered, C for the next one found, and so on. You may ask about planet Proxima A, but the letter A is reserved for the star itself. One thing about the naming convention is that the order of the letters is based on the order of discovery and not their distance from the parent star. So what does Proxima b look like? Proxima b's orbit is tilted with respect to the Earth so that it does not make transits across the disk of the star. As such, scientists could not use the planet detection method of NASA's Kepler mission using blocked starlight to see it. Instead, its existence was deduced from the 11.2-day wobble it produced in the radial line of sight velocity of the star as the planet orbited. At the time of the discovery, scientists also discovered weak evidence suggesting a second planet, which turned out to be correct. Proxima Centauri is a dim red dwarf star and only has 12.3% of the Sun's mass. It also has only 14.1% of its radius and only 0.17% of its net energy output. As a consequence, its habitable zone must be rather close to the star. Like most small stars, Proxima Centauri is relatively unstable, and it is known to produce frequent large solar flares. Its corona temperature is quite low, 3042 Kelvin, as compared to 5772 Kelvin for our Sun. Most of its emitted light is in the infrared rather than the visible. For this reason, it's so dim that even though it's so close, you can't see it in the Earth's sky with the naked eye. Alpha Centauri's relative coldness leads to reduced support of its stellar material against the pull of gravity, resulting in a very high density. The Sun has a density of 1.41 times that of water, but Proxima Centauri's density is about 56.8 times that of water and 7.23 times that of iron. With a mass 129 times greater than that of Jupiter, Alpha Centauri has a diameter that is only 1.5 times that of Jupiter. The planet Proxima b sits rather close to Proxima Centauri, just about 5% of the Earth-Sun orbital distance, or 0.05 astronomical units. This means it makes one complete orbit, or one Proxima b year, in only 11.2 Earth days. However, due to Alpha Centauri's very low energy output, the average surface temperature of Proxima b is within the range in which water should be liquid on its surface. Proxima b is tidally locked to Alpha Centauri. What does this mean, and what are the consequences? You probably know that the Sun and Moon exert tidal forces on the Earth's ocean. This type of force depends on the mass density of the producing object and on the power of the third object's angular size in the sky. Even though to an observer on the Earth, the Sun and Moon appear to have about the same angular size, the Moon's tidal influence is triple that of the Sun because the Moon has 3 times the Sun's mass density. Now, because Proxima b has such a small orbital radius, the star Proxima Centauri, even with its smaller diameter, will seem to have a 2.86 times larger angular diameter in the sky than does our own Sun, as viewed from the Earth. Proxima also has 40 times the density of the Sun. That means the tidal force of Proxima Centauri on Proxima b will be 939 times greater than that the Sun exerts on the Earth. So most likely, Proxima b remains tide-locked to Proxima Centauri. This means that, like Earth's moon, Proxima b would always present the same face to Proxima Centauri. The consequence is that Proxima b will have a desert-like hot side and a deep frozen cold side at the same time. But there will be a twilight zone band around its mid-region in which the star is always just above or just below the horizon. In this region, the temperature won't be extremely hot or cold. But then a tidally locked planet has its advantages. For example, if humans were to live there, it means solar energy farms would always generate electricity. The electricity will then be distributed to other parts of the exoplanet where it's needed. Colonists can just select a location with any average temperature they wanted and could hide from the periodic solar flares by keeping dangerous Proxima Centauri just over the horizon and out of harm's way. However, the colonists will have to cope with less sunlight. The light that your human eye can see, the visible spectrum, has a wavelength ranging from about 400 nanometers at the deep violet edge to 700 nanometers at the deep red edge. However, the sunlight from Proxima Centauri peaks at 950 nanometers, which is well into the infrared, and falls off rapidly in the visible region, with the visible light strongly skewed toward the red. So if light from the Sun and Proxima Centauri were equal at the red edge of the visible spectrum, the light from Proxima would be 10 times weaker at the violet edge. So don't expect to get a nice tan by lying on a beach on Proxima b. This will, of course, affect agriculture. Photosynthesis using chlorophyll works maximally at twin wavelengths of around 470 and 660 nanometers and cuts off to 0 for wavelengths longer than 700 nanometers. So if you take plants from the Earth to Proxima b, they can photosynthesize with only a small fraction of Proxima Centauri's sunlight. But there is a way out to ensure you get fresh food continuously. Silicon solar cells producing electric power have peak conversion efficiency at around 700 nanometers and drop to zero at 1100 nanometers. So you might be able to carry out farming on Proxima b by placing large solar energy farms, soaking up 700 nanometer light on the hot side of the planet and growing plants in twilight zone greenhouses illuminated by electrically powered LEDs producing the 470 and 660 nanometer wavelengths. But what about gravity on Proxima b? Just like the Earth, this exoplanet produces gravity. Proxima is at least 1.3 times that of the Earth and, well, could be much more. If Proxima b is spherical with a mass of, say, 1.5 Earth masses and about the same mass density as Earth, Proxima b's surface gravity would be about 1.145 g, or 11.22 meters per second squared. So you push the scale about 14% more than on Earth. But there is another variable that can change our calculation significantly. You see, the Earth has a relatively high density because of its iron-nickel core. However, Proxima b, like Mars, might not have such a core. So if, because of this, Proxima b has the same mass density as Mars, or 3.93 grams per cubic centimeter, Proxima b's surface gravity would then be 0.866 Gs, or 8.5 meters per second squared, and you would weigh 14% less than on Earth. But then Proxima b may not be spherical. The strong tidal forces would tend to give the tide-locked planet an ovoid or egg shape, with a long axis pointing at the star. So any habitable zone would be located in the mid-region of the ovoid, where its radius would be the smallest, meaning the habitable mid-region would be closer to the planet's center. Here, the surface gravity would be higher than in the hot and cold zones. If the radius was 10% smaller there, the gravity would be 20% larger. Proxima Centauri has frequent solar flares, and there is debate about whether the resulting ionization would strip away any atmosphere that Proxima b might have. It has been argued that if Proxima b has a molten core like the Earth and rotates on its axis every 11.2 days, this might be sufficient to generate a planetary magnetic field that would protect the atmosphere. Even if there is no native life on Proxima b, it may turn out to be an advantage. This is because many arbitrary branch points in the evolution of life could have resulted in life evolving on other planets very differently from what we have on Earth. This type of alien life would be very likely to be toxic to humans. So for a colony site, a sterile planet might be preferable to a biologically hostile one. Such pre-sterilization might make it easier to transplant some simplified version of Earth's ecosystem to Proxima b. Now, why are astronomers interested in the Proxima b exoplanet? To understand this, you need to know its location. Our nearest neighboring star is the Proxima Centauri, located about 4 light-years away. Just like our Sun, Proxima Centauri has its own set of planets orbiting it. One of the planets is the Proxima b. This exoplanet was discovered in 2016 and has intrigued scientists ever since then. Scientists have also discovered Proxima c and Proxima d, although Proxima d is still awaiting confirmation. However, much of the attention has been on Proxima b for good reasons. Because the planet orbits right in the middle of its star's habitable zone, it's possible that liquid water and potentially even life could exist there. Because of its Earth-like mass, scientists believe that not only could liquid water exist on Proxima b, it could also be a rocky, terrestrial planet similar to Earth. Proxima b orbits around a star that, while close to our solar system, is also much dimmer and much less massive than our Sun. The exoplanet is tidally locked and in synchronous rotation with its star, meaning that one side is always facing the star and one is always facing away, a light side and a dark side. In addition, it's unclear if Proxima b has an atmosphere. However, if Proxima b has an atmosphere, the simple ingredients, water, carbon dioxide, and rock that are needed for the formation of biochemical cycles that we call life could all be present and interacting on the planet's surface. The planet lies very close to its star, completing one orbit every 11 Earth days. The temperature on the surface of the planet could be between -90 degrees and 30 degrees Celsius, or -130 and 86 Fahrenheit. Scientists are intensely looking for life outside this planet, but how exactly do they look for life on these distant planets? Water is present on Proxima b. However, scientists don't know for sure the amount of water Proxima b had initially, but their calculations have shown that Proxima b could have lost about 1 ocean's worth of water due to the early irradiation in the first 100 to 200 million years after formation. What happened after that period is still under investigation. Perhaps this Earth-like planet continued to lose significant amounts of atmospheric gases, or perhaps it's been able to keep most of its atmosphere and preserve liquid water on the surface, making it hospitable to life as we know it. Scientists have even discovered where most of the water on Proxima b might be located, which would be handy if one day you might find yourself stranded on the planet. By examining the possible climates using a sophisticated 3D model and exploring a wide variety of atmospheric compositions and water inventories, it was discovered that liquid water might be present over the surface of the planet in the sunniest regions, either in an area in the hemisphere of the planet facing the star or in a tropical belt. If James Webb is able to detect the narrowband light that is reminiscent of LED bulbs, it will be because it will be able to characterize the atmosphere of the planet. This will allow researchers to use instruments on the observatory to detect how much energy transport occurs on the planet and then perform calculations of light curves to determine whether they match those of an LED light source or not. To come to the conclusion that it may be able to detect artificial light, Loeb and colleagues use the JWST exposure time calculator. This tool allows astronomers to predict what can be detected in any given time period based on predefined settings before the observatory launches. It allowed them to determine the possibility of detecting different flux values and detecting those with a wavelength that matches artificial light levels that should be expected from a civilization forced to live in permanent darkness. In that case, the lights shining onto the permanent night side should be extremely powerful and thus more likely to be detected with JWST. The JWST will be able to show the existence of artificial illumination for standard LEDs 500 times more powerful than those currently found on Earth's, and for artificial illumination of similar magnitude to Earth's. Of course, crewed missions may be impossible, at least for now, but Project Breakthrough Starshot is attempting to develop tiny nanoprobes that could maybe go at 10% or 20% the speed of light to visit the Centauri system. This mission is supported by Russian billionaire Yuri Milner. It may take decades for the probes to arrive at Proxima b, but they will surely help us uncover more secrets about the exoplanet. When the Breakthrough spacecraft arrive at Proxima b, will they find aliens waiting for them? Turns out we have been receiving signals emanating from Proxima Centauri, which raises many possibilities. It all started with a strange signal picked up by the 64-meter Parkes radio telescope in Australia while it was observing Proxima Centauri. Astronomers were using Parkes to catch radio emissions from powerful flares shooting off the star. The detection was made by a $100 million project called Breakthrough Listen, led by Andrew Simeon from the University of California, Berkeley, and funded by tech billionaire Yuri Milner under the umbrella of Milner's Breakthrough Initiatives. The goal of this multi-year endeavor, which began in 2015 with a star-studded announcement attended by Stephen Hawking and other space science luminaries, is to buy observing time on radio telescopes around the world to search the skies for evidence of technological civilizations. That pursuit is more commonly known as the Search for Extraterrestrial Intelligence, SETI. Using Parkes, the astronomers had observed the star for 26 hours as part of their stellar flare study. But as is routine within the Breakthrough Listen project, they also flagged the resulting data for a later look to seek out any candidate SETI signals. The task fell to a young intern in Simeon's SETI program at Berkeley, Shane Smith, an undergraduate student at Hillsdale College. Smith began sifting through the data until he stumbled upon the curious narrow-band emission, needle-sharp at 982.002 MHz, hidden in plain view in the Proxima Centauri observations. From there, things happened fast. It's the most exciting signal that we've found in the Breakthrough Listen project because we haven't had a signal jump through this many of our filters before, says Sophia Sheikh from Penn State University, who helmed the subsequent analysis of the signal for Breakthrough Listen. Soon the team began calling the signal by a more formal name, BLC-1, or Breakthrough Listen Candidate 1. Although the press reports are unclear on exactly how and when Parkes detected the signal, it apparently showed up during 5 30-minute periods over several days, all while the telescope was pointing directly at Proxima. Breakthrough Listen uses a technique called nodding, where the telescope will spend a period looking at a target and then an equivalent period looking elsewhere in the sky to check that any potential signal is truly coming from the target. In 5 of the 30-minute observations over about 3 hours, we see this thing come back, Sheikh says, a hint that the signal indeed originated from Proxima Centauri or some other deep space source in that part of the sky before making its way to Earth. Notably, when the telescope was turned away from the star, the signal vanished. Ultimately, the signal's origin appears tightly constrained within a 16-foot wide circle, roughly half the size of the full moon, around Proxima Centauri on the sky. Breakthrough Listen employs software filters capable of rejecting the cacophony of signals originating from Earth or Earth-orbiting satellites to isolate those coming from deep space. But this transmission was unlike anything the project had previously encountered. Team leader Andrew Simeon told Scientific American that it had some particular properties that caused it to pass many of their checks and struggled to explain it. Most curiously, it occupies a very narrow band of the radio spectrum, 982 MHz specifically, which is a region typically bereft of transmissions from human-made satellites and spacecraft. We don't know of any natural way to compress electromagnetic energy into a single bin in frequency, such as this one, Simeon says. Perhaps, he says, some as-yet unknown exotic quirk of plasma physics could be a natural explanation for the tantalizingly concentrated radio waves. Speaking on the significance of the discovery, Jason Wright, a SETI-centric astronomer at Penn State University in Pennsylvania, said, "If you see such a signal and it's not coming from the surface of Earth, you know you have detected extraterrestrial technology." While work is still ongoing to analyze BLC-1 to confirm whether it came from aliens, nothing stops scientists from turning the JWST on Proxima b. What is interesting is that some scientists have been trying to determine if the new telescope will be able to detect artificial light, which is a definite sign of civilization on Proxima b. Working on the assumption that aliens on the exoplanet would use LEDs similar to what we have on Earth, Elisa Tabor of Stanford University and Abraham Loeb of Harvard University concluded that if the artificial night-side illumination of Proxima b reaches 5% of the natural day-side illumination, JWST could detect the artificial light with 85% certainty. In further research of the possibility of life on Proxima b, scientists have also tried to determine what the Earth as a planet would look like if it was orbiting Proxima Centauri. They relied on modeling to work out what the situation would look like. Again, we return to the concept of habitable zones. Just because Proxima b's orbit is in the habitable zone, which is the distance from its host star where water could pool on a planet's surface, doesn't mean it's livable. It doesn't take into account, for example, whether water actually exists on the planet or whether an atmosphere could survive in that orbit. Atmospheres are also essential for life as we know it because it allows for climate regulation, the maintenance of water-friendly surface pressure, shielding from hazardous space weather, and the housing of life's chemical building blocks. The scientists' computer model used Earth's atmosphere, magnetic field, and gravity as proxies for Proxima b's. They also calculated how much radiation Proxima Centauri produces on average based on NASA's Chandra X-ray Observatory observations. With these data, their model simulates how the host star's intense radiation and frequent flaring affect the exoplanet's atmosphere. An active red dwarf star like Proxima Centauri strips away the atmosphere when high-energy extreme ultraviolet radiation ionizes atmospheric gases, knocking off electrons and producing a swathe of electrically charged particles. In this process, the newly formed electrons gain enough energy that they can readily escape the planet's gravity and race out of the atmosphere. Opposite charges attract, so as more negatively charged electrons leave the atmosphere, they create a powerful charge separation that pulls positively charged ions along with them out into space. In Proxima Centauri's habitable zone, Proxima b encounters bouts of extreme ultraviolet radiation hundreds of times greater than Earth does from the Sun. That radiation generates enough energy to strip away not just the lightest molecules, hydrogen, but also, over time, heavier elements such as oxygen and nitrogen. The model shows Proxima Centauri's powerful radiation drains the Earth-like atmosphere as much as 10,000 times faster than what happens at Earth. To understand how the process can vary, the scientists looked at two other factors that exacerbate atmospheric loss. First, they considered the temperature of the neutral atmosphere, called the thermosphere. They found that as the thermosphere heats with more stellar radiation, atmospheric escape increases. Let's hear what you think of life existing on Proxima b in the comments section below.